Now that we have seen how pipelines work and how they are affected by hazards and dependencies, let's talk about how many stages a pipeline should have. In the pipelines we have seen so far, the ideal CPI is 1. We will later in this course see pipelines where the ideal CPI will be larger than 1 because they try to do more than 1 instruction per cycle. But regardless, there is some ideal CPI that the pipeline should be achieving, and it boils down to executing some number of instructions every single cycle. Now let's consider what happens when we add more stages to the pipeline. We get more hazards this way. We have already seen that some of the dependencies cause the number of stalls or flush cycles that depend on how deep the pipeline is. For example, if a branch is resolved in the second or third stage of the pipeline, we only have to flush 1 or 2 instructions that we have incorrectly fetched. If the pipeline, however, resolves branches in something like 15th cycle, then we will flush 14 instructions when we have a branch that we incorrectly resolve. So we have more hazards when we have more stages, and what that does is it adds more of that CPI penalty. So the CPI increases because of that penalty that we have when we have a hazard. But with more stages, there is less work per stage, which means that our cycle time can be decreased. Less work per stage means that every cycle there is less work to do, which means we can do it in less time, so we can speed up our clock. We already know the iron law, which says that the execution time is equal to the number of instructions times the CPI times the cycle time. If we have the same number of instructions, because we're just trying to figure out for the same instruction set whether we should have a processor that has more or fewer stages, if we increase the number of stages, our CPI goes up, which increases execution time, but the cycle time drops, which decreases execution time. So the number of stages needs to be chosen in a way that balances the CPI and the cycle time. You don't want to have too few stages, because then your cycle time will be too long, but you don't want to have too many stages, because then your CPI will be too high. We can plot the number of stages here and how execution time depends on it, and this is what it looks like. As you increase the number of stages, the execution time drops because you still don't have too many hazards, but you're improving the clock cycle time. At some point, you get fewer benefits from reducing the cycle time, and the CPI increase starts to hurt. Beyond some point, you are no longer shortening the cycle time very much, but you're suffering a lot from hazards that are now causing dependencies that cause many, many cycles of stores or flushes. So the bottom of this curve for modern processors would be at something like 30 to 40 stages, which would be a very, very deep pipeline. So this is if you only consider performance. So for performance, we want a pipeline that is 30 to 40 stages deep. But we need to consider power. If we add more stages, we are shortening the cycle time, so we have more cycles per second. And in each of those cycles, we now have more pipeline latches that spend energy latching temporary results. So power quickly increases with the number of stages. If we plot power, it does something like this. So because of performance and power considerations, we want to choose something that is not in this performance optimal point. We want something that is also power efficient. So we end up with 10 to 15 stages in modern processors. So again, this is not because performance is best when you have this many stages. It's because it's the number of stages that balances pretty good performance with relatively low power consumption, or at least manageable power consumption.